Sponges are a reasonably well understood group of modern animals, so it might be surprising that there is an entire major group of fossils that we don't quite know what to do with. However, they're almost certainly really important. Hello again. As many of you have probably realised, I'm quite fond of sponges. They are kind of my thing, they're my main specialism, and so I've been doing quite a long series of videos trying to get into early sponge evolution, their relationships, and their history. And this is quite important for understanding early animals, which is my other really main interest, and how they relate to other phyla and the whole geological transition between the Ediacaran and the Phanerozoic, the Cambrian and Ordovician. So they fit in a very important place in the history of life because they are one of the earliest groups of animals to branch off from the rest of them. So it's important to understand them. And sponges have generally been misunderstood and overlooked, in my opinion, and this is an attempt to redress that balance, an attempt to try to get an understanding out there which is a little bit more nuanced than the things you will find in textbooks. So a lot of the previous videos I've done on this have been about the origins of the demosponges, the heteractinids, two of the four modern living classes, and a few real oddballs in the Cambrian which have implications for how we fit things together. But this one is an attempt to tackle one of the other two remaining classes. So the other two are the homoscleromorphs, about which we understand almost nothing of their origins. They have virtually no fossil record, a few spicules from the Carboniferous onwards, and that's about it. They don't seem to fit in morphologically with anything else. It's a mystery. We just need a lot more information on that. And then the last group is the calcareans. Now, the Calcarea are a class that has long been recognised as a distinct group of sponges on the basis of several major features. They have a skeleton made of calcite spicules. All of the others, if they have spicules at all, are siliceous, so made of opal. In the Calcarea, they're spicules, which are tiny little needle-like structures that make up the skeleton, thousands of them all interlocking and arranged in beautifully delicate ways, are made of calcium carbonate. High magnesium calcium carbonate, which is important because it is much more soluble than low magnesium carbonate, which means that they're less likely to survive as fossils because they dissolve. And those spicules generally are tiny. So you can go and find calcareans today around modern seashores, even around the UK. They wash up on the beaches, normally attached to the bases of seaweeds. So go after a storm and you can find lots of little tiny white sponges, which are very easily overlooked. Some of them are a millimetre or so in size, but you get them under the microscope and they are really beautiful things. And these are quite a major group. I think the taxonomy is a nightmare, so estimates of species numbers are probably a bit mixed, but it's certainly in the hundreds of species, maybe getting towards 1,000 worldwide. And there's a lot of revision needed doing because they're difficult. And they are generally inhabitants of shallow water, usually rocky coastlines with lots of attached seaweeds, sometimes caves, things like that. They're not so abundant at all in deep water environments where you're likely to get better fossilization potential. They are extremely small for the most part, either that or they're massively encrusting onto a hard surface where they have virtually no preservation potential. And the skeletal elements themselves are tiny. So when you see one of these, think about the fossil preservation potential, and as a paleontologist, you start just sort of going on to something easier because there's virtually no chance of these being preserved intact. Mostly. There are also hypercalcified calcareans. Now, these are ones in which the spicules are embedded in a wall of aragonite. So they actually have a massive layer of aragonite, which then leads to the reduction of the number of spicules, sometimes to complete loss of spicules. And you end up with something which looks completely different, but is at least fossilizable. And so we have a few groups of these, and they are recognized in the fossil record from the Permian onwards. There are various groups of them that have gone down this path of hypercalcification, and in the Mesozoic there are reasonable numbers of these calcareans that actually have a skeleton which is fossilized. And they can become quite major sort of reef-building organisms even, so that they're not something to be dismissed at all. But for my interest, which is mainly tracing the history backwards, they're kind of irrelevant, because they're all secondarily hypercalcified. They're all minor groups within the tree that have evolved this adaptation independently, created this massive skeleton and become fossilizable. But they're not telling us anything about the ancestry of the group as a whole. And worse still, when you turn into a sort of hypercalcified form, you tend to lose most of the morphology that you had beforehand. So we can't even go back to these ones and look at their, even their Triassic origins and say, well, this is clearly derived from something that looked like that. Because as they evolve this type of skeleton, they modify quite radically from what they were before. So we're left with the modern calcareans, effectively. There are also some Jurassic spiculate calcareans, some things that look like the modern ones. Not very many of them, they're extremely rare. There are supposedly some carboniferous ones, a thing called Protoleucon from Russia, which it's not compelling to me, I don't think. I think there's just not enough certainty over whether that is related to Calcarea at all. It's a strange thing, and it's potentially really interesting, and it probably deserves another look and someone analysing it with much more high-resolution imaging and so on to try to make sense of it. But at the moment, I think we can basically say that these modern spiculate calcareans have no Paleozoic fossil record of any significance at all. But what do the modern ones look like? Well, we have a wide range of body forms, actually, in terms of the architecture of the body wall. So there are quite a lot of encrusting forms, there are a lot of tubular ones, and it's normally some sort of variation between them. Sometimes they're branching, you can have a mass of tubes forming one sort of colony, but many of them, and many of the simplest ones, tend to be solitary, effectively. They're tubular things with an osculum at the end and radial or slightly squished radial symmetry. Now, the internal architecture of these, the structure of the body wall, is actually quite varied. In fact, there is quite often used a classification of the architecture of sponges called ascon, cycon, and leucon, depending on how complexly folded and internally cavernous the body wall actually is. And these are all based on calcareans. Technically, you can't apply them to other groups because they don't quite have the same structures. Similar forms of architecture have evolved in, for example, edemosponges, but you've got these three types who are actually defined on the Calcarea. And it includes the simplest of them all, which is this ascon form, in which it seems to be a body wall composed of a single layer of spicules supporting it. And then there are no chambers, there are no exhalant canals. You just have the inner surface of the wall is covered by these choanocytes, the feeding cells with a flagellae. So they're the ones that are catching the food, creating a current, and forcing the water out the osculum at the top. And this is often thought to be the probably ancestral type of skeleton and body wall architecture, because you can't get much more simple, and everything else seems to be a modification to increase the efficiency of the feeding process. That said, it is possible that the ascon forms are, at least in part, secondarily simplified due to small size. So something which would not be efficient in a large sponge works perfectly well in a small one. So it may be that there's a bit more complexity there. The next grade up is the cycon phase, where you have an ascon body wall and then you fold it, sort of in and out, and then that partly encloses some areas which become exhalant canals leading into the centre. And then a more complex form again is when you lose all the folding and you just have isolated feeding chambers joined up by little canals, which then eventually lead into the central cavity. So it's quite a complex array. But the ascon in particular, that skeletal type, the very thin wall of spicules in a sort of cylindrical body form, is very reminiscent of what we see in some of the earliest fossils of sponges, where you have an extremely simple thin wall of spicules of various types, whether they're more apparently closely related to hexactinelids or whatever, but that is the type of architecture that all of the classes of sponges go back to. So you have the hexactinelids, you trace them back, they become something more like a reticulosan with a very simple thin wall, a regular grid of little hexactin type spicules. The demosponges, you can trace back to a thinner and thinner wall until you end up with something like Crumulospongia. All of these things seem to trace backwards to an ascon-like architecture. Of course, we don't have the soft tissues in these, so we can't be absolutely sure that these things were ascon, but the body wall support system in the skeleton doesn't seem able to support much more than that. Now, on a final note, there are some extra types of architectures that you get only in calcareans. So one is a Celaeobid, which is quite interesting because there's a thing called Carduispongia that we'll come back to from the Silurian that seems to have a Celaeobid architecture. We'll come back to that one. In terms of the skeleton, what these spicules are, I've said they're made of calcium carbonate, high magnesium carbonate, but the central part doesn't have a filament like you get in the siliceous sponges, but the central part of the spicule is generally amorphous calcium carbonate. Then it reverts to normal calcite. So you have potentially a differentiation at some point within the spicule, and you can actually see that there is a transition that occurs during the spicule development, which again will become important later on. There is also the aspect that they are secreted, unlike the siliceous spicules, which are onto an organic template in this filament in the centre. They're secreted by an external organic lamina. So it's got a sort of a sheath surrounding it, which is extremely thin, extremely delicate, virtually unfossilizable, but it's there. And you can get preservation of this potentially. Okay. Spicule forms. They're not very big, I mentioned that, but they are generally of three types. You have simple oxias, so very simple needle-shaped spicules, one axis. You have triactins, which are three axes in one plane, like a propeller. And then tetractins, which have four rays going out in different directions, kind of like that. So you have three. There are no two in any one plane, three going out like a sort of tripod, and then one sticking directly up. And these are your basic types. There is an anomaly. There is a thing called cycon pentactinoides, in which you have not triactins, the three in one plane, but five rays. And this is some weird anomaly of that species as far as we can make out. It's not a common feature of the class at all, but it's interesting. For various reasons we'll come back to. Okay, so in these previous videos we've been discussing how, in my view at least, there is a lot more continuity of the fossil record of sponges than is normally given credit to. So if this is completely new to you, you might want to check some of the other videos first. But the basic idea is that most people have assumed, and many biologists still assume, and some paleontologists even, that mineralization occurred separately in each class of sponges, that they had ancestors that joined up, but they were all soft-bodied and totally unfossilizable. and that everything that we find in the fossil record can therefore be squeezed into one of these classes, or to an extinct class potentially. What we've been arguing for years is that, in fact, you can interpret the fossil record as being these hidden bits of the tree, and they can all join up quite neatly to give you a fairly coherent evolutionary history with the species that we have in the fossil record already. But that means that spicules are shared between classes, and that means including the siliceous and calcareous spicules, they can be homologous structures, despite the fact that they have different mineralogy today. So we have this concept of bimineralic spicules, which there is significant evidence in the fossil record, in the Cambrian especially, showing that there were sponges, anomalous sponges by today's standards, which have spicules made of a silica core surrounded by a layer of calcite. And in some cases, this is unambiguous. In others, we need more evidence because it's hard to get the preservation. But they certainly existed, and it's a question of how widespread these bimineralic spicules were and how significant they are. Now, so far, I've been looking mainly at tracing the living classes backwards and looking at one or two complete oddballs and then sort of general characters like the distribution of hexactins. Today is slightly different in that we're kind of tracing it backwards, but then you hit a dead end because we don't have things that look like modern calcareans in the fossil record before about the Jurassic, really. And then there are things that have been interpreted as calcareans, which are more ambiguous. So what we're going to look at today is one of these problematic groups of fossils that have been associated with calcareans for a good long while for very good reasons. And we're going to have a really good think about this because I've always assumed that this group are stem group calcareans, that they are on the way towards it. It's just been my default position following other people. But I'm not totally sure anymore. It's time to meet the heteractinids. So the heteractinids, the name comes from heteractin meaning different number of these, because they don't have spicules that match up with anything alive today. The general form of the spicule in heteractinids, and this is really their defining character, is 6 rays in one plane. It has hexagonal symmetry. Quite often there's also a ray going up and down from that plane, so you have what are called octactins, so 8-rayed spicules, but 6 of them in one plane. And there is nothing that does that today. If that was the end of the story and it was really consistent, then we just have to say, okay, there's something different. But there is more to it, because there is quite a lot of variation. And the heteractinids are known from the early Cambrian through to the Permian, I think, is the latest one, but they're basically quite well-known group through the Paleozoic. In the Silurian, they can be some of the most common sponges, and there is quite a diversity of them as well. I mean, they are not universally common by any means. You don't expect to find a heteractinid when you go out fossil collecting, unless you go to a very specific site. But they are well known. They turn up in quite a lot of places around the world. And I don't have any specimens to show you. I have described one or two, and I've worked on others in museum collections, but I've not actually found any in recent years to have as in my teaching collection. So it's something that you look forward to finding, and you're quite glad when you do. A classic example, the sort of archetypal one, if you like, is a thing called Astraeospongium. Now, this is found in Silurian reef sediments in particular, also in the Devonian, I think possibly in the Ordovician as well, that genus. It's quite a wide-ranging one. And it has a massive sort of bowl-shaped skeleton composed of these hexaradiate or octactin spicules. And those spicules are very densely interwoven together, and they are often indeed cemented together as well, so it's partly hypercalcified. There is a degree of cement which is binding these spicules together into a solid form. But they are by no means the only one. And you get a wide range of other things which developed a even more cemented skeleton with taller morphology or wider bowl-shaped, various variations on it. They're all basically radially symmetric. But the number of rays on the spicule varies quite a lot. And in one group in particular, the Weewalkelidae, they have ended up as being triactins. So you have a skeleton of calcarean-like triactins, which are all bound together and cemented into a massive skeleton. And the reason that these are considered to be related to modern calcareans is that these spicules are calcitic. And it's better than that, because sometimes they're preserved really quite nicely. And there's one paper by Mell and Reitner and Mell, one or the other, which showed the internal structure of these basically effectively mimics that of what we see in modern calcareans. So you have that internal division into two types of calcite, one of which recrystallizes and the other tends to stay more pristine. But you have a division within the spicules in the same way that we see in the modern calcarean spicules. So it's a pretty good indication that you have calcite spicules with the same calcite structure, with the same triradiate architecture or form as you get in calcareans, is all a pretty good indicator that you're looking at something similar to calcareans and probably their ancestors. Makes sense, right? Well, yes and no. Because although there are no other living sponges that have calcite spicules, that doesn't mean that there were no other sponges in the past. And of course, if the bimineralic spicule argument is correct, you could have had multiple lineages evolving these calcareous spicules just by losing the siliceous part. But did they? Or is this actually an ancestor of calcareans? Well, there are also differences. So the architecture of the body wall of these doesn't match Ascon or Psychon or really Leucon that well either. It seems to be its own very massive structure with canals meandering through it. It's very irregular sort of organisation, which doesn't really match up with what we see in the modern calcareans. Also, the spicules may look similar, at least the triradiate ones, but they're gigantic in comparison. So you've got things that have triradiate spicules, but they're, 2 orders of magnitude? At least one, larger than anything in the modern. So this should give us some sort of cause for concern. And then you have to start thinking where these fit in the tree. Now, Keith Rigby and Matt Nitecki have done quite a lot of work in the past, back in the 1970s mainly, on the evolution of this group, because it's quite a nice self-contained group, and you can see trends in the morphology of these sponges through time. You see them becoming more triradiate dominated and much more massive skeletons and much more cemented as you go through time. But that means that we can also trace them backwards, of course. And this is where it starts getting particularly interesting for me, because as with all the other classes, if you trace them backwards, you end up with something which is thin-walled, delicate, single layer of spicules, unfused, globose with an osculum at the top. It's exactly the same sort of pattern as we see in the Heteractinids and demosponges. It goes back to something really quite delicate. And the best known of these is a thing called Eifelia. Now this actually is something I have a bit of a soft spot for, because it was my first really significant paper on sponges back in 2005, when I was looking at a specimen of Eifelia globosa from the Burgess jail, which is quite a well-known genus. It had been described 3 times by then. Walcott in 1920, Rigby in 1986, and then Rigby and Collins 2004 as well. And you look up the description, it has an array of spicules of hexaradiates only. And I was looking at this specimen and thinking, so what are those hexactins doing there? Because there were quite clearly a substantial number of cross-shaped spicules in amongst the skeleton. And although these rocks are flattened and the specimens are flattened and the spicules are decalcified and demineralized, you can still see their little sort of nubs sticking up and down in some of them as well. So these were actually hexactins. They had rays going up and down as well as being just 4 in one plane and 6 in one plane. And this shouldn't have been there. So I ended up going to the Smithsonian Institution to look at the type material and found that these spicules were in every single specimen they had, including the holotype of Ifelia globosa. It's just that they'd been totally overlooked. These things that should be absolutely classic heteractinids, hexaradiate spicules only, actually have hexactins in. And it got a little more complex than that because the arrangement of these spicules is quite striking in that you have a wide range of sizes and the distribution of them is such that if you take any of the large-sized spicules and then look for the next smaller size, it fits into the gap between the larger ones. And you can then go to the next level down. You look for those smaller ones, or the second size, and you look for the gaps between them, and you find the next smaller, and so on. And this is something that is a pattern that we see universally in early reticulocens. So things which have been ascribed to hexactinelids in the past, and which we argue are paraphyletic. So they are an ancestral group that gave those to quite a lot of other sponges, maybe all of them even. And so we have here what is called the quadruled pattern, containing hexactins in a body form that looks just like an early hexactinelid, as they call them. So in this case, we have something that looks like it is morphologically continuous with the ancestors of hexactinelids and demosponges and so on. And yet it's also morphologically continuous with these unique hexaradiate spicules, with other members of the Ipheliidae, and then the Astraeospongiidae and all the other heteractinids. It's a continuum. So there are intermediates within this continuum. It's not a perfect continuum, but there's no reason to doubt that Ifelia is a member of the same group as the other heteractinids. This, of course, leads to quite a lot of conundrums. Not least those homoscleromorphs. Because according to molecular phylogenies, the sister group of Calcarea is not Cilicia, it's homoscleromorpha. So this is this odd group of, to non-specialists, extremely poorly known sponges. They have either tiny little spicules, little tetractins of silica, or they have no skeleton at all. They're virtually entirely encrusting onto hard surfaces. They're usually found in caves and places like that. And they are relatively poorly known, even among biologists. They weren't even recognised as their own class until 2012. Before then, they were lumped in with demosponges. But they don't share any similarity at all with heteractinids, or indeed really with modern calcareans. And it's if the heteractinids represent the stem group of Calcarea, then it's very hard to see how you can go from somewhere in that lineage to something that looks like a homoscleromorph. We have to assume, I would guess, that there has been radical modification of homoscleromorpha from its ancestral state, that maybe it went through some sort of bottleneck, maybe it went through some sort of morphological bottleneck, that it became highly specialized in its ancestral form, lost most of the features that you would want to see, and then redeveloped a skeleton independently. That's actually the most likely scenario here. But it does mean that we can't really fit those in. And so, like most people, I tend to ignore the homoscleromorphs as much as I possibly can. Don't get me wrong, they are lovely. And they do contain some really, really interesting features. like relic things like a basal cell membrane that suggests that sponges might have once had an epithelium. Yeah, it's this one really oddball derived group that seems to share a feature with other animals that has been lost in other sponges. Doesn't make much sense. They're a weird group. But back to the heteractinids. One can imagine it's relatively easy to evolve from something like Ifelia into something with purely hexaradiate spicules and eventually triradiate, with some pentaradiate and other things going on somewhere along the line as well. Partly because there is a link between crystal symmetry and spicule form. Now, crystal symmetry in calcite is triradiate. So one of the most energetically sensible ways of making a spicule is to make use of that and have a triradiate spicule. There is a pretty clear energetic argument for why that would be correlated. That if you have calcite spicules, there would be a tendency for them to become triradiate or hexaradiate, of course, is a related symmetry pattern. So that is an argument that you might have multiple parallel evolution of triradiate spicules, and that is likely to happen within things with calcite spicules. Going back to Ifelia, though, I mentioned before that there are bimineralic spicules of various types in the early history of sponges. And one of those cases where we haven't been able to be quite certain, but it looks like it, is in fact Ifelia. So in the Burgess Shale, everything's demineralized. It's all metamorphosed, leached. You don't get the original preservation of the biominerals very well at all. And in something as small as a spicule, even a big spicule like these, you're not going to see it. And yet we do see a relic of something interesting going on, even in the Burgess Shale. And there we have examples where there is a central area which seems to be differently mineralized to the outer part of the spicule ray. There's even a difference in relief where the ends of the spicule, or the edges, are preserved a little bit differently to the center where it seems to be more flattened, almost as if the inner part was dissolving more easily than the outer part. It's not been possible to prove it from the Burgess Shale. From isolated Ipheliid spicules, though, there is more direct evidence in that some isolated spicules have been found in which there is evidence for an original axial space, a canal, which in some cases is filled with silica. Now, that apparently is secondarily crystallized silica, so we don't know what it was originally. And unfortunately, all this has never been published, which is a real shame. It's never been published properly. There was a bit of an aside in Stefan Bengtsson and Des Collins' monograph on the Chancelloriids. That was the only time it was mentioned in passing that there is a canal in the centre of these spicules, which implies that there is probably different mineralogy. However, that issue with the central part of modern calcarean spicules being different to the outer part in terms of being amorphous carbonate versus calcite, at least at various points within the secretion of the spicule, means that we can't be 100% sure that that's not what's happening. So we need more information, and if anyone's got some nice isolated Ipheliid-like spicules from the Cambrian, please do see if there's any internal structure in them preserved, because that would be really handy to actually resolve this. But there is certainly some at least striking evidence that these could have been bimineralic. We just can't prove it for certain. Of course, when you've got one lot of anomalies, the best thing to do to try to resolve them is to look for more anomalies. And this is the fossil record, so there's plenty to go around. Now, there are a wide range of early sponges, particularly Cambrian ones, that are difficult to tie in with other groups, but there are some which have been assigned, at least tentatively, to the calcareans. So one lot is the Nuchidae, the wonderfully named Nuka, Wagima, and Jawonya. These are mostly Australian, hence the names, but they are really interesting little things, and they're very small, vase-shaped structures with a reticulate, mostly solid wall of calcium carbonate. And there are gaps in the wall, but embedded within this solid hypercalcified skeleton are little spicules that include heteractinids. So these seem to have the same sort of spicule form, albeit quite a lot smaller, familiar, and yet they are quite different in structure. It looks like a separate origin of hypercalcification. And they all have this weird neck at the top of the sponge around the osculum, like a vase. It's quite an interesting structure, which we don't get in any heteractinids. So these have been suggested to be calcareans, on the basis that they have calcarean-like spicules, and they kind of almost match the general sort of body form, but not really. There's nothing else quite like them, but they do have these heteractins. There are also another group which is entirely Cambrian from all over the world, actually. I think they're quite widespread, called the Palaeontologist. Now, these are fundamentally based on spicules which are trivadiate, so again, typically calcarean sort of feature, but then two of the rays, or sometimes all of them, branch again. So you have this rather odd morphology of spicule, which has been found isolated in quite a few locations. But we've never found a complete one. At least there's never been one published. I actually have found an articulated one, but this was back when I was living in China, and there's politics of working with different research groups and what you can publish and what you can't. So that's sitting in somebody's collections somewhere in China, but it's not brilliantly informative, but there is a bit of articulated skeleton of one of these polyactinelids, showing that it was kind of Eifelia-like, I guess, which is not what you expect somehow, because it's such a distinctive spicule morphology, but it looks like it's a modification of that sort of thin body wall, dense mass of spicules overlapping, interlocking with each other. So we've got a range of things that might be related. They all have unique features, and they all share in common calcite spicules, which have at least trivadiate symmetry and in many cases hexavadiate. It's difficult to see all these evolving from modern calcareans or even from the immediate ancestors of them. But if calcite spicules were a common feature among early sponges, and if there is an energetic link between calcite spicules and trivadiate or hexavadiate symmetry, which makes a lot of sense mineralogically, then it's entirely possible that you have these each evolving independently from something which is more related to Eifelia. So something which is primitive in its body morphology, a very thin wall with basic trivadiate to hexavadiate spicules, and they each take this basic form and evolve in different directions. And that's kind of how I'm thinking of these things, because you can't find really clear links between Wagima or Polyactinella and modern calcareans. It just seems that they've all taken some basic feature and evolved in different directions from it. So, most of the recent assessments of heteractinids have concluded that they are probably somewhere in the stem group of calcareans, plus or minus homoscleromorphs wherever they fit in. But there's still also the view, which has been included in the recent treatise in 2004, that they are a separate class and they just leave it there. So what we have, and trying to piece together the evidence for this, is we have a link to calcareans in terms of the spicule symmetry, mineralogy, and structure. But if that spicule mineralogy and structure is primitive, then the morphology would potentially follow from that as well. So it doesn't follow that they are close to the crown group end of Calcarean. They could be much, much deeper, going back to somewhere with the link to the other classes, or it could be something which has evolved multiple times from something which just shares a fundamental feature like spicule mineralogy. There's too much uncertainty there to know exactly what to do with them. We do have the links to reticulosans in Iphelia, with these hexactins in a reticulosan-like array of spicules. And that, to me, is pretty strong evidence that these things are actually originating very close to the other classes, or to the common ancestor with them. And then we have things like Carduispongia, which causes absolute chaos by having a reticulosan-like skeleton. I've mentioned this one before, so I'm sure you remember it. Which has a regular square grid of hexactin spicules, absolutely typical morphology, but we know that those spicules were originally calcite. Better still, we have the soft tissue, and it's coleobid type. So just like we see in some modern calcareans. So if you're going from an early group of sponges on the stem leading towards Calcarea, which are heteractinids, how do you then revert to something like Carduispongia, which has purely hexactin spicules, but has soft tissue that looks like Calcarean? There's reversals going on there in order to get between them, and then a reversal again to get back to triradiate spicules like we see in the modern Calcareans. Homoscleromorphs, again, a complete enigma. The spicules that they do have are tetractins, so there is potentially a link there to what we see in the Calcareans, but their tetractins are siliceous, with a sort of diffuse axial filament structure like you get in Cilicia. So again, that doesn't really make sense for having that as an intervening bit between a sort of stem group of heteractinids, then homoscleromorphs branching off, and then calcareans. There's too many reversals. We've got things like the Nuchidae, which may be related, but there are major modifications happening between whatever their ancestors were and what we see in the fossil record. So at the moment, they are still an enigma. We don't know where the heteractinids really fit. If the heteractinids are completely separate in their spicule morphology, they've evolved them totally independently from what we see in modern calcareans, then they don't have to be restricted to the stem group of Calcarea plus homoscleromorpha. They could have evolved from somewhere else deep in this early history of sponges, maybe from within the stem group of Cilicia, where you have the various reticulosans. And if there were bimineralic spicules at the base of the crown group of Porifera, then there would have been this calcitic element leading to the modern Cilicia, and that could indeed evolve in this other direction. And the heteractinids would then be almost a red herring. They're telling us that there was a lot more diversity in the groups of sponges that were evolving from the basal sponges. But they're not telling us directly about the origins of Calcarea. And I think my best guess at the moment is that they branched from somewhere in that basal complex of sponges, and we don't know where. It's possible they came from the very early stem leading to Calcarea, but in that case, probably the hexaradiate spicules are not meaningful when it comes to the origins of Calcarea. Because we have between them and modern calcareans probably things like Carduispongia, which were purely reticulosan-based. And we have the homoscleromorpha fitting in somewhere as well. I think the message really from the heteractinids is that we have here quite a well-known group of fossils, and people have tried to fit them in to various places like the stem group Calcarea, including ourselves, or they have just said, they're different, separate class, leave it at that, and not worried about them anymore. And I think the real story here is that they are an important group of sponges, but we don't yet understand where they fit, and we have to recognize that. Because the best way of making sense of this, in my view, is to have them from a slightly unknown point on the tree, but very close to the base of crown group sponges. And we need more analysis, more information on these very early groups of sponges. We need more information on mineralogy. We need to see which ones are bimineralic, which ones were originally calcareous. We need a lot more papers coming out on the details of these weird early things. Polyactinellids, Nuchids and so on. Can we really look at the fine detail of these and understand them properly in order to try to resolve some of the relationships among these early sponges? Because, once again, just to reiterate, this point about whether the sponges biomineralized independently in each class, as most of the biologists would have us believe, or whether they have a shared ancestry which will speculate, is absolutely critical to our understanding of the earliest animals. Because if sponges have a shared skeleton, then that skeleton should be easily preservable as far back as their origin. And if our understanding of the origins of sponges based on molecular clocks is correct, and these things have a really deep ancestry, then that leads to a whopping great contradiction in the fossil record, because we are then missing spicules, biomineralized structures from the entire Ediacaran. Our view, which we've been proposing for a while now, is that we really need to take seriously the view that sponges diversified and even originated as part of the latest Ediacaran to Cambrian explosion. That this is a pattern that we see through all of the modern phyla, and possibly with excepting Cnidaria, which may have a slightly deeper root that's recognizable, but not by much, and even that's ambiguous. But it would mean that the Ediacara biota as a whole is something else. So we're kind of tackling this on this channel from all angles, really trying to analyze what the Ediacaran biota is telling us, how much we can tie that in with the living animal phyla, to even the branches of the tree leading to the animal phyla, but within the crown group of Metazoa. And also looking at the sponges and trying to trace them backwards and making sense of their fossil record, because there are huge mysteries that we think are being glossed over. And there you have it for heteractinids. At the moment, we can't fit them in properly. We have ideas, but we can't prove them. And if we could only resolve what exactly the heteractinids were, I think it would help enormously with resolving this question of what the earliest crown group sponge looked like, whether it had a skeleton, and therefore its implications for Ediacaran paleontology. Sweet dreams. I'll leave it there. And maybe we'll go on to bryozoans next. Not sure. Got a very busy week coming up now, but we'll be back fairly soon with something else interesting. Thank you again for watching. Thank you once again to all my lovely members who are supporting the channel that way. And if you haven't seen any of the back catalogue on sponges, you might want to. You might need to watch them a few times as well. There's quite a lot of information in there. Bye for now.